My name is Tyler Hughes. I'm a graduate student at Washington University in St. Louis. Today I will be telling you about two models that we have recently developed for predicting the toxicity risks of drug-like molecules. Now, many adverse drug reactions are caused by electrophilic drug metabolites. These electrophilic metabolites conjugate to endogenous nucleophilic sites such as DNA, proteins, or lipids, and can cause a variety of problems. For example, it is well known that an overdose of acetaminophen leads to hepatotoxicity. This hepatotoxicity is actually due to metabolism of acetaminophen into the electrophilic metabolite NAPQI. NAPQI is electrophilically reactive and conjugates to nucleophilic sites in proteins, such as cysteine residues. This forms what is known as a hapten complex because it looks foreign to the immune system, and the subsequent inflammatory response is actually responsible for acetaminophen's hepatotoxicity. So today I will be telling you about two models, the xenosite reactivity model and the xenosite epoxidation model, which both aim to attack this pathway at two different levels. First of all, conjugation with glutathione is actually an important defense mechanism to this toxicity pathway. Glutathione, which is outlined here in gray, is a tripeptide with a central nucleophilic cysteine. Glutathione is actually the most abundant peptide within cells and conjugates to small electrophilic molecules, allowing them to be secreted from cells, thereby protecting cells from the damaging effects of these small molecules. However, glutathione is subject to depletion. For example, an overdose of acetaminophen can reduce hepatic glutathione by up to 90%. And this leaves one vulnerable to further small electrophilic molecules or generalized oxidative stress. An important ramification of this is also that if a small molecule is reactive with glutathione, meaning that it conjugates to glutathione, this small molecule will also likely be a toxic molecule. And this is the motivation for the xenosite reactivity model, which is the first method that we're aware of that is able to predict both atom level and molecule level reactivity to glutathione. What we want to do is take any input molecule, put it into the xenosite model, and predict both where glutathione will conjugate on the molecule and if that molecule will be reactive as a whole with glutathione. We recently had this work accepted in chemical research and toxicology. So the first part, predicting sites of reactivity, is actually really important because it helps you understand the mechanism of a molecule's toxicity. For example, with NAPQI, we've circled that atom in red because that's the specific atom to which both protein and glutathione binds. And if you know these sites of reactivity, it can help you modify small molecules to potentially make them safer. So to attack this problem computationally, we needed experimental reactivity data to model. For this, we went to the Accelerus Metabolite database, which is a collection of literature-derived chemical reactions. From this database, we extracted 1,200 molecules for which we know their exact sites of reactivity. We've put up 4 examples here with their atoms of reactivity circled in red. We also wanted to model on the molecule level whether or not a molecule will be reactive and therefore toxic. With this in mind, we extracted 271 non-reactive molecules which are closely related to reactive ones. Because as you can see in the case of acetaminophen versus NAPQI, they're very similar chemically. They only differ by 2 hydrogens, yet we know they have very different toxicity profiles. So an important test our model is to distinguish such cases. When analyzing our data, one thing we were struck by is how structurally diverse reactive molecules actually are. For example, there are 2 common motifs called microacceptors and epoxides. I visualized examples of these on the right. These are all well known to be reactive. However, even if we filter our training data set against all of these structures, we still were left with the majority of our molecules. So I put up 9 examples here on the left of different molecules that don't have any of these structural alerts, but are still known to be reactive with glutathione. So one of the challenges of our model is predicting reactivity across a wide range of chemical space. So let me tell you about the structure of the xenocyte reactivity model. I'll tell you how information flows through the model. We start with the molecule layer, we can call our sample molecule X. We have a 3D structure of this molecule from which we calculate a variety of chemical descriptors. These are simply mathematical ways of describing molecules. They can be at both the molecule level and the atom level. Examples of molecule level descriptors might be molecular weight or a measure of its hydrophobicity. Atom level descriptors can be both topological and quantum chemical. Topological descriptors encompass simple connectivity information such as what atom are you, what atom are your neighbors, are you in a ring, what size ring are you in. Quantum chemical descriptors describe electronic information about the atom's electronic environment. We calculate these using MOPAC with an implicit solvent model and PM7 force field. After we calculate these descriptors, we will then flow into the hidden layer, which is going to be 10 hidden knowns. I've only visualized 2 here for clarity. The output of the hidden layer will be an atom reactivity score, or ARS. This is a probabilistic measure of how likely an atom is to be a site of reactivity. Finally, the top 5 atom reactivity scores within each molecule, as well as all molecule level descriptors, flow into the final molecule output layer, which outputs a molecule reactivity score, or MRS, reflecting the probability that a molecule will be reactive with glutathione and therefore toxic. Now, we're first going to focus on training the model at the atom level. So we're going to focus on the atom reactivity scores. We will label atoms as reactive or non-reactive with glutathione, and we will train the model in cross-validated experiments so as to assign reactive atoms with high ARS and non-reactive atoms with low ARS. To assess the performance of our model, we will use the average site AUC metric. Let me explain to you how this works. The molecule on the left, we can see, is predicted well by our model because the experimentally observed site of reactivity, which is circled in gray, is actually receiving the second highest prediction of all atoms within that molecule. If we calculate a ROT curve across all the atoms within the molecule and measure the area under the curve, we get a performance of 0.95. This is close to perfect, with perfect being a score of 1 and baseline being a score of 0.5. In contrast, the molecule on the right is predicted poorly by our model because the experimentally observed site of reactivity, circled in gray, is relatively lowly predicted in comparison to other atoms within the molecule. So the ROT curve here will give an area under the curve of only 0.71. So if we pretend that our entire data set is encompassed of only these 2 molecules, we can just average these 2 AUCs and report it as a percentage to get 83%. So this is just a toy example. But if we do this across our diverse data set of 1,200 reactive molecules, the cross-validated atom reactivity scores actually have a high accuracy of 91%. So 9 out of 10 times, if we know a molecule is reactive with glutathione, we are ranking that reactive atom above all other reactive atoms, or non-reactive atoms within that molecule. An important point of comparison here are quantum chemical descriptors, such as self-polarizability and nucleophilic and electrophilic delocalizability. These are reported in the literature to be very important for reactivity at the atom level. And we can see that they do have moderate predictive power, with self-polarizability getting up to almost 75%. But clearly, when we consider a wide variety of chemical attributes in concert with machine learning, we are able to offer a much more informative prediction of which atoms will actually be reactive with glutathione, as evidenced by our performance, which improves by about 15% over self-polarizability. So it's furthermore encouraging that we are actually able to predict reactive sites, even those that are not in commonly accepted structural alerts. So here are those same 9 examples of diverse molecules I showed you earlier, this time with their with the predictions visualized, as evidenced by the strength of the red shading. And you can see that in each case, the most highly predicted atom within each molecule is actually its experimentally observed site of reactivity. So we were very encouraged by our ability to identify sites of reactivity, because this gives an important indication as to the mechanism of a molecule's toxicity. I'm now going to transition to the molecule level and focus on whether we can identify molecules as being toxic as a whole. So here are those same example molecules, but now we're circling whole atoms as reactive, and then these are going to be non-reactive molecules. And again, we'll train our model and cross-validate experiments, aiming to assign these reactive molecules with a high MRS, and all other molecules with a low MRS. To assess performance, we will use the molecule AUC metric, which simply calculates a ROC curve across the entire data set. Ideally, if the model works well, we will see reactive molecules with a much higher MRS than non-reactive molecules, which ideally will score lower, even though they're structurally similar. So this metric in cross-validated experiments gives a performance of about 80%, as evidenced by the MRS, the red bar at the top. If we again compare to individual quantum mechanical descriptors, they're not performing nearly as well. The best of which is the negative, the energy, the lowest unoccupied molecular orbital. But that's only accurate about 65% of the time. Another important point of comparison are quantitative structural activity relationship models, or abbreviated as QSART models. These are typically trained on very small data sets and aim to fit simple equations to the reactivity and toxicity of these molecules. Most of these QSAR models are not applicable to a wide range of chemical space. We did find two, however, that are based on the energy of the lowest unoccupied molecular orbital and are trained on the reactivity and toxicity of 10 benzoquinones. But as you can see, when applied to our structurally diverse data set, these two QSAR models only have an accuracy of about 65%, whereas they actually have really high training data on their own training data set. But our model offers an advantage in that we can apply it to a wide range of chemical space. Now you might notice here that the accuracy at the molecule level is 80%, whereas actually on the atom level was 90%. And we think that that is a symptom of the quality of the data. Here, a lot of our non-reactive negative training examples might actually be reactive, because when we were picking out our molecules, we simply assumed that molecules were not reactive due to the absence of them being studied in context of the reactivity. So we think the data is a lot noisier, but we still find it encouraging that we're able to outperform all the individual descriptors as well as the other QSAR models currently available in the field. It's furthermore encouraging to us that the molecular activity scores are actually correlated significantly with experimental toxicity and reactivity values. So here are those 10 benzoquinones that were the basis for the QSAR models that I just told you about. We visualized the predictions on these 10 molecules. And on the right, you can see the molecular activity score compared to toxicity and glutathione reactivity. So here on the top, we've got our molecular activity score on the x-axis and the toxicity of these 10 molecules on the y-axis. And you can see that the higher the molecular activity score, the lower will be the LC50, meaning the molecule is more toxic. Similarly, on the bottom, we compare the glutathione reactivity and the molecular activity score. And the higher the molecular activity score, the more reactive the molecule actually is experimentally. So this is surprising and encouraging to us, because it shows that our model is understanding subtle differences in the structure of these 10 molecules, even though they all have the same core quinone structure and simply vary by small substituents at different sites on the molecule. So finally, an important test for our model is, can we distinguish drugs that are known to cause adverse drug reactions from the reactive metabolites that actually mediate these adverse drug reactions? So here are two examples. Trimethoprim is an antibacterial that it has associated with some toxicity. This toxicity is actually due to the formation of the amine methide, which is known to be reactive with glutathione.